So this is the course outline. Another screen. I'm sharing my whole screen so that you can see everything, rather than sharing part by part. So I hope everyone can see this outline. The same is also on the e-learning, so you can have another separate screen. So anyone who can see the e-learning? Okay, fine. And anyone who can see my screen? Okay, fine. So this is our outline. The unit previously was called Artificial Neural Networks and Pattern Recognition, but now we changed the name to Machine Learning, and we'll be using these two names as we intertwine the two names. The reason for this is because of late neural networks and pattern recognition have kind of dominated machine learning. So this is what the unit previously was called, but we felt like the scope needs to be a little bit broader than this one. So I will tie the two. That's why I put both names here. But in your AMS, you might see this one, and then in the register, etc., we see this one, but they're more like the same. So anyway, everything is outlined here. In this course, already we have covered AI, introduction to AI, that is. We've done a lot of probe and stats, linear algebra, calculus, data structures, and algorithms. We'll be using concepts from all these units and all these kind of knowledge areas to be able to do our machine learning. So fine. So why are we doing these units? Because machine learning is like the heart and soul of AI. We have already introduced machine learning, so you actually know what machine learning is all about. And these are the learning outcomes. So very fast, to go to this other side of the outline, you see just what we'll be doing and where we are going to start and how we are going to flow. So we start by exploring the foundations of machine learning, reviewing what we already know, and then taking introductions right here. Then we are going to confirm the things that we installed in our machines that are actually there, and we'll add a few more for NLP and also for computer vision and image processing. This time, we won't just be writing Python as it is, but we'll also try to upgrade and see if we can use other libraries, etc. But generally, we'll just be using notebooks, Jupyter notebooks, and Google Colabs, and we'll be uploading our code on GitHub, and we'll be using a lot of libraries like NLTK for NLP, and Stanford NLP. Those are going to be two. For the other mathematical computations, we use everything in SciPy. Then for deep learning, we'll use TensorFlow, PyTorch, Skitlan, Keras, etc. I might also take you through how to set up servers if we find time, and I don't know, I'm trying to check on that one, etc. So those are going to be our tools, and you can, by the way, go ahead and install these things. You already know how we do the installs, etc. But I'll prepare something small and upload it on e-learning. But before we get there, a very strong review is what we are going to start with today. Then from there, we go to another section that is called machine learning models. We are going to explore models. But actually, before we explore models, so I will interchange these ones, we are going to do something called theory of learning, the theory upon which machine learning is built. Okay, and we'll combine that with regression. So I will talk about what is regression, etc. Then we will explore the models, like some of the models that we already know. Now here we'll be exploring a group of models. Okay, some models are probabilistic, they use a lot of probability. Some are state machines, some are just rule systems, etc. Some are vector models, and I'll be talking about all this as we go on and on. And from there, I will do our cut. I'll talk about this also. Then after that, we go to supervised and unsupervised learning in depth. So we'll be looking at these two in a deeper sense. We'll also return to reinforcement learning, and this time I'm introducing something new called association rules. Then I will take a better part of this course discussing deep learning and how actually to do deep learning. And then I will also check, so I hope everyone is fine here. Okay. So some people are saying I zoom in a bit, but either way, the outline is still on e-learning. So you can also open it as we go through together. So anyway, so in case of any issues, yes, this is how we'll be proceeding. You just flag them here. Okay, fine. My audio is okay. Yeah, someone just comment and then I'll be good to go. Fine. So reinforcement learning, and I will introduce the association rules. This, I'm going to discuss what they are. Then better part of the course is dedicated to deep learning. In fact, like a month or so. So I will slash some time here and then discuss a lot on deep learning, introduction, of course. Then from there, we will tie all these into application areas, mainly in NLP and computer vision and image processing, which are large areas of AI that are actually part of the most difficult. So we're just going to appreciate projects in those areas, and then we will be good to go. So either way, let me see here. The rest you can just check. They might change with time. No big deal there. The books are also here. I'm going to share more for those who want to read in a deeper sense, etc. So basically, in a nutshell, that is our outline, which can also, the same copy is already on e-learning. Okay, fine. Any major concerns on the outline? I don't think so. So I think we are good to go. Okay, fine. Good. So from the outline, we just take a dive and we start immediately. So here I'm going to zoom how much better so that you see. Okay, fine. Okay. Okay, so this is loading, so don't worry. Let me see. Let's see. Okay, fine. Okay, fine. Let me just open a new one totally. Okay, good. Okay, these notes are also there on e-learning. Fine. So this is where we start. The foundations of machine learning is our first topic. And we have an agenda here. This is how we are going to flow for this week and also next week. We were supposed to meet on Monday, but though Monday was a holiday. Okay, fine. So first we are going to do a recap. Okay, we're going to do a recap. So if you are already joining us now, we have already done the course outline. So head on to e-learning. The enrollment key is deep blue 2020. Lowercase, no spaces. Okay, fine. So we are going to do introduction, revisited, of course, because we had already introduced in introduction to AI. Then we are going to look at statistical versus classical machine learning. Then from there, we branch immediately into modern day machine learning, which is basically statistical. Then from there, we will check out a few application areas, and then we will prepare for our labs. So that's the flow of this first 2 weeks or so. Fine, so let me now go to, we revisit the introduction very fast. I won't take much time here because we already know the introduction. Okay, so the introductory notes here. Okay, fine. Okay, so we have where we are starting, colored in red, machine learning introduction revisited. And here we are starting with, yes, introduction to machine learning. A quote there from the father of AI. What we want is a machine that can learn from experience. That was said by Alan Turing in 1947. So we're actually going to build on that quote as we go on. So, of course, you already remember quite some things on machine learning. I want guys just to tell me generally what you remember from machine learning, particularly from our past AI class. So when you want to comment, you just turn on your mic, then you talk, and then I will hear you. Then I will amplify your comment, and then participation will be real. So anyone to call in and tell us something you remember and something profound about machine learning from our past classes. Who goes first? We have both groups, A and B. Anyone out there? Those are a way to confirm that guys can hear me. So if I call you, don't run away. Good. Who remembers anything in these tough and difficult times? Everyone is here anyway. Stacy, are you there?
Yes, I'm here.
You can hear me?
Yes, I can hear you.
How are you?
I'm fine. How are you?
I'm good. It's good news to hear that you're fine. Of late, we are not taking anything for granted. Do you remember anything in this machine learning story? I know you remember a lot.
Okay.
Yes.
About the components like actuators, agents.
Yeah. Very good. There was something called an agent, right? And okay, thank you for the comment. There's an agent. Then the agent.
So the agent perceives the environment.
Yes, the agent perceives an environment from where they get data.
Yes. And then they could act on the data using actuators.
Yeah, they could act on the data using actuators. Thank you very much. So there's an agent who actually perceives the environment and then processes the data or learns from the data, and then actually they can act on the environment. That was like machine learning or just AI in general. Okay, fine. That was Stacy from Group A. By now I know almost everyone, 90%. We can now talk to maybe Jaden. My friend, are you around and safe?
Hello?
I hope you can hear us.
Hello?
Yes, how are you?
Fine, thank you.
Yes, I can hear you.
Oh, okay.
You're good?
Yeah, I'm good. How about you?
Yeah, I'm fine also. That's good news. Any comment from the past class concerning machine learning or AI in general?
I remember machine learning was one of the major branches of artificial intelligence, along with NLP and knowledge-based systems and robotics.
Yes. Yeah. Very good. Yes. So machine learning is one of the major areas. In fact, I will say machine learning sits at the center, and then all other kind of units borrow a lot from or use a lot of the models that are in machine learning. Thank you very much, Jaden. Fine. So we'll be participating as we go along. So let me just rush through this one as I remind you some of the things we said last time. Anyway, so this field of AI or now machine learning particularly and specifically, we talked about agents, the way Cecilia said, and these agents actually, they are perceiving the environment, and then they are getting data. Then this data is going to be used as a past experience. And then what is learning? That's the question we are going to answer in these other next slide. So anyway, the idea here is to be able to learn from past experience, but we don't define a word using the same word. So we are using the word adaptable. Okay, so the agent must be able to adapt. So when things change, it should be able to adapt on its own. The other keyword we were using here is the word called autonomy. So if I may circle some things here, the keyword that I might circle here or highlight here is actually, let me just get in a little bit larger. The keyword here is actually to adapt to the environment, to the changes. So the rest is revision. Adaptation is the main thing. So that's what you're being reminded. So different from traditional computing, AI systems are able to adapt to a changing environment with autonomy. Autonomy means it needs very little supervision. It works on its own. So autonomy is borrowed from the word independence. So it is actually like the machine is independent. They are free. So freedom is in quotes. Okay, fine. So what exactly is learning? Is this aspect of improving. Okay, so the machine is able to kind of improve its performance. That is like the main thing here. The improving of performance over time, of course, as it consumes more and more data, it is able to improve. Okay, fine. So learning is by improvement of performance. So this means, circle that one. The mouse is not perfect. So this means there are some three things that are important whenever we want to do learning or machine learning. There is a task, of course. That task is task T. Then there's some data set, of course. We will call that experience. Then very importantly, there is something called a performance measure. Okay, so this performance measure is actually what is supposed to tell us, is this machine learning or it's not learning, because it must improve its performance. And we actually used various ways to measure performance. Who remember what we used to measure performance in supervised learning? Which technique did we use? You can just name it or shout it or something like that. Mm-hmm. How did we measure performance of models? Okay. Performance of models, anyone who can remember? Marvin, my friend from Group B, can you hear me? Marvin?
Yes, I can. Yes, I can.
How are you?
I'm fine. Can you hear me?
Yes, I can. I hope the rest can also hear you. Yes, you remember performance measure?
Yes, I do. So,
yes. Can you give us some hints?
For performance, it was based on the accuracy of the model and also how many out of its required tasks, how many have been able to have been executed. Sorry.
Okay, so there was the element of accuracy, and then the opposite was error rate.
Rate, yes.
Yes, accuracy versus error rate, etc. So we want to increase accuracy but to reduce the error rate. Very good. Anyone else who remembers what we actually use specifically? We drew some things. I hope someone can remember there was a confusion matrix. Okay, that is one of the ways. There's a confusion matrix. That was like the major way, by the way, we looked at of measuring error. Now we are going to introduce some good mathematics for measuring error as we move on. So I will teach you a lot on how to measure this performance. One of the ways was actually the confusion matrix. Very good. Fine. So these are the main things in a learning environment. Good. The rest you can read on as you remember. So for example, if we were doing computer vision, a task could be, we want the machine to identify objects. We'll actually do this one a lot. And then how do we define accuracy? Like the way Marvin says, the number of objects that are correctly recognized, okay? And then what is the experience is the data that we actually feed into the system. Very good. So with that, that is like the recap to be able to, from what we did last time. So we now move to the next agenda, unless there is a question. The next agenda is statistical machine learning versus the classical machine learning. Good. So let's dive into this one. So modern day machine learning is kind of confused with things like data science and maybe even data mining, etc. Now we are going to kind of clear the air concerning these as we actually even start. So machine learning is actually deeper than what we call data science, etc. And we are going to see in what ways. So the key idea here that we are going to see, and there's a saying here by Newell here that you can actually read through. Physical symbol systems as the necessary sufficient means for general intel. I will discuss that in a moment. But now, it's like we are trying to track down the history of machine learning very briefly and very fast, just for our knowledge. So it is as deep as the history of AI. By the way, AI is just a field born out of computing, which was born out of a world war, specifically World War II. By the way, great things happen immediately after tough times, like world wars, most of the inventions, by the way. So even as we go through this unprecedented time, all is not lost. This is the opportunity to research, etc., etc. So actually, this is a post-World War II era. Machines are introduced, computers, fast computers, etc. But AI just starts to kick in like a decade later, when guys say that these machines can actually learn on their own. You don't have to cram this one, just have to understand it. And this is just for our knowledge. Unless you want to become a machine learning historian or an AI historian also, which is also good. So anyway, so you can check through this, but these are the major eras. Early works laid on the foundations in the 40s, birth of AI is in the 50s, AI starts to solve problems, general problem solvers in the 60s. None of us was there, even me. Emergence of expert systems. You remember KBS, and the reason why we said, the reason why we are not knowledge-based engineers, because the thing collapsed. This is going to be the story, by the way, in this section. Because KBS falls under what we call the classical machine learning part. And then in the 90s, in the 80s, there's a period we call the AI winter. There was no funding here. Government said we don't want this AI thing. Businesses were not funding research. Research is funded by governments and also by businesses. So guys said this AI is a hoax. We are tired of it, etc. So in the 80s, AI was kind of in a winter age. Then in the 90s, again, guys were back in business. And then here we started having things like SVM, support vector machines. We'll discuss them. Then in the 2000s, this is the era of big data. The internet was massively growing, etc. And it was like a new decade. Then in the 2010s, this is where deep learning was well born, etc. And data has already increased in the world. And these are going to define like the main areas or main eras in AI. So very fast, I just have please open these ones in your machines. If they are not clear, I'm very sure. Right here, you can see just a timeline, which is actually very important, but almost similar to what we have looked at. You can look at the major things that took place from the 50s to 2017. But some of the major things you can see, like, let me see, when neural networks were starting to boom, like in the 80s. In fact, it was neural networks that brought in the AI winter. I will discuss what happened, one of the major challenges, and it was actually what brought AI back later. And currently, as we are speaking, some of the major things in the field is actually deep learning, which is driven by neural nets. Good. Another timeline is here from way back in the times of Aristotle and these philosophers, all the way to logic that we are going to use a lot, all the way to Turing and Church writing their thesis paper. Turing was a student of Alonzo Church, and this is the origin of the Turing machine and Turing paper, master's thesis, and then first computers, and then the first neural network in the 40s, all the way to deep learning in the current times. Okay, that's going to be the flow. Then here we just have, this is actually and arguably the most important slide in this section, history of models. I want you to carefully look at this graph and then see how models were kind of emerging and disappearing. When it first started in the 40s, it was linear classifiers that were actually the talk of town. And this is how linear classifiers were moving. They dominated the 40s and early 50s. In the late 50s, the first neural network, which is called Matlock, and the Matlock network was kind of invented. Then neural networks started to spike, and at this point, they were able to overtake Now neural networks here were not actually called neural networks, they're called perceptrons. And then they declined later in the 60s, etc. Then the real neural networks were emerging and going all the way. So here you're able to see some of the major models that we'll actually look at, from linear classifiers all the way to deep learning models that you can actually see here. So currently we're in 2020. You can see this is one of the latest graphs. And you can see a period just about late to maybe 2007 thereabout. That's where deep learning was starting to gain. And you can see the rise and the rise and the rise of deep learning. You can see support vector machines. They were powerful in the 1990s, etc. And these are going to be our major models. So please always have this in at the back of your mind. We moved from linear classifiers to perceptrons to neural networks to the invention of backpropagation to support vector machines. Now we're in the era of deep learning. Good. So fine. After that, now because deep learning is the new sheriff in town, then we have now like the flow. How did we get to deep learning, etc. So in deep learning, we'll be discussing things like recurrent neural networks, deep belief networks, convolution neural networks. We'll start by this thing called the XOR problem. Is actually what brought the AI winter later. We'll see what that problem is and we will solve it because it has already been far solved. All the way to long short-term memories, LSTMs, all the way deep into the history of deep learning. By the way, deep learning is not one model, but it is a class of models. So please look at those graphs and then you'll be good to go. So back to, as we finish this section very fast. So there's what we call classical machine learning, which can also be called symbolic AI. Okay, then there is the modern day deep learning, modern day machine learning that is dominated by deep learning. So the idea here is to show that machine learning is not statistics and machine learning is not deep learning. Machine learning is broad, but current and modern day machine learning uses statistics and deep learning and a lot of probabilistic systems. So that's where we are currently. So the idea here is that you see how history was moving. By the time perceptrons were being introduced, some guys were still on linear classifiers saying we can't move on, this is how AI has to be done, etc. So this was a defining moment, and so is every other defining moment. Now we are in deep learning, and many guys are studying deep learning, but I don't like to study one particular model alone, because come tomorrow, you might find another model now rising beyond deep learning. And then guys who are in deep learning will struggle saying, oh, deep learning is the way to go, etc. So machine learning is not equal to deep learning. But modern day machine learning runs on deep learning models. Deep learning, we will see the reason why. So classical AI or classical machine learning is the AI that uses symbols. If you remember KBS so well, we were just using symbols, okay, and truth tables, etc. So this AI fell because of the reasons that we are going to say. So this is the philosophical debate. Thomas Hobbes, who is the father of neural nets, etc., and backpropagation, by the way, this is the main guy in neural network learning. What the guy says, thinking is manipulation of symbols. By the way, that is the real thing. Our brain thinks by manipulating symbols, okay? And reasoning is computation. Some guys were saying thinking is the manipulation of symbols, and that's how the human brain is working. So to be able to have smart machines, we must be able to represent symbols and manipulate symbols at the same time. And it goes all the way back to some famous philosophers like René Descartes, who is a very famous French philosopher, etc. He's also a mathematician. This guy also, this is in the 16th century. sharing. The guy really talked about these symbols. So the issue here is majorly symbols. That's why it's also called symbolic AI. This is like the main thing. Okay, so we need to represent symbols and manipulate the symbols. So what is thinking? It's the algebraic manipulation of symbols. That was traditional AI. Good. So that's the main thing. It's also called symbolic AI. Some people believe there was no machine learning during this time, and it's a valid argument. Good. So the thing here is that for us to be able to build smart machines, we have to look at a model. We have to look at human beings. How do they think? How do they reason? And can we actually be able to re-engineer that one? And that was like the main thing. So very fast, let's go through this one. We finished this one. There's another famous guy. This guy is still alive. Study a lot of him in NLP because that's his major field. The argument he puts out is that humans are born innate with certain set of structural rule systems. So by the time you are born, your brain somehow has some rules that are already pre-installed according to Noam Chomsky. Like when you look at language and grammar, it's like an order and a pattern. And guys are like born with it according to Chomsky. But another philosopher says that man is born tabula rasa. Tabula rasa means that you're just born empty, then you learn from experience. So even if it's grammar, you learn from experience. So the debate goes on both sides. These are very famous philosophers, John Locke, Noam Chomsky, etc. Rosso, and all these other guys that you might want to look at their work. So why did symbolic AI fall? So the key problem here is what we pointed out in knowledge-based systems, okay, KBS. Like, for example, representing common sense became so difficult, okay? Roger Penrose says that there is something quantum mechanical going on in our minds or our brains that modern day physics can't explain. So if physics can't explain it and maths can't explain it, then we can't model it. That's why algorithms in AI, they are called models. Okay. What's a model? A model is a representation. It's not the real thing, it's the representation of the real. Call them models in AI. We are going to see mathematical models, probabilistic models, etc. So representing common sense. So this is the slide you should focus on in this section. I could ask you to justify why modern day AI is driven by statistics heavily. So the argument here is that this symbolic AI, it was difficult to represent symbols. It is difficult to represent common sense, okay? And learning was almost impossible in this period. Some people even believe there was no machine learning at this time and age. So this is symbolic AI. There was no learning at this time and age. So that's like the main idea that you should capture. Symbols difficult to explain. Copying the human mind became so difficult, and then symbolic AI actually collapsed. That's why now guys moved into a lot of maths and statistics. So the argument here, as we summarize, is that if we followed everything from nature and we wanted to build an aeroplane, then all planes will have wings that are flapping. Okay, that's like the argument. Or all cars, instead of tires, cars will have legs and they'll be running around, which is actually like a joke. So this is like the main argument. Symbolic AI fell because of these reasons. Now, symbolic AI has fallen. We have buried it. Now, it's time to go to modern day AI, which is actually now called statistical machine learning. It's the area of data science and big data. That's the current data, the current period we are in. And this is actually what we are going to study a lot, statistical machine learning. So what is statistical machine learning? Very fast, we can look at this slide. Machine learning theory built upon statistical framework, okay? And this is going to be our model throughout the rest of the course. Any question, you can just type them there on the chat. I'll be able to kind of look into it. Fine. So I want to introduce statistical machine learning. Then we are good to go. If you have a question, feel free to put on your mic and then to actually just talk to me. So modern day AI, driven by statistics, data, and a lot of math. So why statistics? We are going to see that in a moment. So this should be obvious since machine learning involves data and statistics is the mathematical branch that handles data, or it's well defined that statistics is the science of data. So modern day machine learning is based on statistical learning theory. That's why you guys learned a lot of statistics and probability, etc. So that is what we call, or I call, statistical machine learning. Now, there are some areas of AI that are even some areas of machine learning still that are still learning or running on traditional AI or classical AI. Especially in NLP, we have a lot of algorithms and models that are still running, and that's what the world is currently still using, running on traditional AI. Anyway, I'm going to go through this fast. Please take notes. I'll mention a lot of things and ask questions if you have them, because I'm going to summarize statistical machine learning using a supervised learning example. Okay, so this is a statistical machine learning. So let's use a supervised learning as an example. So it tells us this. What is data? It is a set containing some x's and some y's. Okay, so it is a set. It is a set of n data points. Then the attributes of the data, they are called the features. I hope you remember features. Okay, and then the values of the features are provided by x, which we are going to represent as a matrix. Remember us drawing some matrix in neural nets? We are going to use a lot of that. And then these features are mapped by a certain functions to give us the output. So there's features which has values. There's a function that maps the x to the y's, okay? That maps the input to the output. Then the statistical learning theory for machine learning says that we know that we have this data. Our goal is to find this function, okay? That is learning. Learning is to discover this function that is mapping x to y, okay? So when we are starting, we have some candidates of this function, okay? So there are some candidates that we are looking out for of this function. So the function is like the main thing in this machine learning story. So we want to find it. So the possible functions are going to form candidates. In statistics, those candidates are called the hypothesis space. Very good. So the story continues. To find these functions, which maps x to y, we have to make the algorithm to learn. Okay, learning must take place. So how does the algorithm learn? Learning is tracked using a loss function. So there's another function called a loss function. Okay, it's function number 2. It's called a loss function. So these are the keywords of machine learning, by the way. If you can have them down, they'll be good. There's a loss function. There's data. Data has features, and then there's liking place. And you actually want to discover the true function that is mapping x to y. So for each hypothesis that we have, we need to evaluate how the function performs. There is a performance measure, okay, the one that we were talking about. Okay. How do we do it? There's an error rate to be measured, and this error rate is actually found by finding or optimizing the loss function using calculus theory, which we are going to revise in a moment. So this is now the story of machine learning. from the data to the X and the Y sets, that's supervised learning. And then you want to discover the function that is mapping X's to Y's, the inputs to outputs. So you have to learn that function. You have a loss function that is tracking how your algorithms are learning. And then you're tracking it using the performance measure, which is actually the error rate. And we're going to be finding this one using calculus. I will tell you how. 5. Then the story continues. 2 more slides to the end of the story. In fact, it's the final one. 1 more slide. However, the algorithm has the tendency to cheat in order to minimize its loss function by overfitting of data. There is a problem called overfitting of data, which we talked about some time back. So what is to overfit? To overfit is to be too specific to the training data, such that when you are given another data that you have never seen, which I call truly unseen, then the algorithm will not perform well. So there's a machine learning joke that you train on a data set, then you test on the same data set, then you see that your model is 99.9% accurate. Then you say, this is a model like no other. But when you give that model another data that is truly unseen, that it has not seen before, it will not be able to perform well. Okay, so we actually train on a portion of data we call the training set. Then we validate on another different portion that is called the test set. That is the entire machine learning story, from the data to the function to the loss function to the optimization of the loss function, trying to minimize the error, to avoiding overfitting, to having training and test sets, etc. This is what we are going to do. So you see, actually, statistical machine learning captures everything, okay? Everything. So I just thought I should tell that story for you to be able to see the big connection. And now very fast we are going to go towards the modern machine learning. So does anyone have a question so far on this statistical theory of supervised machine learning? I could ask you to construct the same for unsupervised machine learning, and you'll actually see the flow. It's almost the same, etc. But for now, we can go now. How did we get to modern AI? Please go through this. There's like a small table you have there. Yours is clearer than mine. And just see the major inventions towards the modern day AI. This is very important. In 1763, Bayes' theorem was developed by Thomas Bayes, he was a priest. And there's some notable priests who have been able to do some nice inventions in history. Thomas Bayes is one of them. Mendel is another one. You might have studied him in biology, etc. And Bayes' theorem is the foundation of modern day AI. In fact, Bayes was so humble that he did not publish his work. So it is his friend who published his work later after Bayes had died. So we are going to see Bayes' theorem, and we have actually introduced this. Then Markovian chains. Andrei Markov is a Russian mathematician, and we are going to use Markov chains for a lot. Alan Turing, the father of modern day AI, an English scientist, Turing machine. First neural networks in the 50s. Marvin Minsky, a very famous name of AI. In fact, these are the guys who started AI and coined the term AI, and Dean Edmond, who is actually my relative, I think so. Then the perceptron, etc. So go through these major inventions. I will just point out on some. You see, like recurrent neural nets. They were developed in 1982 by John Hopfield. Okay, another famous name in AI. Backpropagation, the one that we were using to train neural nets, it was discovered in the 70s. Look at where KNN and nearest neighbor models are falling. These are in the 60s. Okay, these are the major inventions that I thought I should put here. Then in the medias in the 80s, so you look at all this, reinforcement learning was well coined in 89. Random forests were introduced in 95. Let's turn off our mics. Okay, fine. Okay, I hope that one does not mute my mic. Okay, fine. Then support vector machines in 95. Then in 97, IBM Deep Blue was able to beat, this is Kasparov, Andrei, the Russian guru. Then LSTMs were introduced in 97, long short-term memories, a type of neural nets. We'll look at these ones. Then finally into our times, very fast. In 2002, a major library was released. It's called Torch. It was called Torch. Nowadays we have PyTorch. Torch was in C and C++. Then Facebook made PyTorch, which is now a Python extension. Then after Torch and PyTorch came, and then libraries, Spencer and Keras were later released. These libraries are actually massive pieces of code that are developed by very many developers, of course. Then Google Brain managed to do something in 2012. The algorithm able to recognize cats on YouTube might sound funny and silly, but this is not easy. Computer vision is one of the most difficult areas of AI. Then 2014, Facebook published their work on DeepFace, which is facial recognition software. You have actually seen it on Facebook trying to recognize your face or trying to tag people. The project was called DeepFace. You can see these are massive tech companies sponsoring some massive projects, etc. And then 2016, AlphaGo did also something, and the story continues. So that's like the journey to modern day AI and how statistics is playing the major role. Very good. We are done with a lot of introduction and theories. We are now meant now to go into the real stuff. I hope you have your writing materials. I just want to take some major questions. All this that you have discussed today is not for cramming. Please don't try cramming. I won't ask you what happened in 1763, but I just want you to know how this thing is flowing, a very deeper sense of the history of AI. Very good. So now we have agreed that as we are doing statistical machine learning, that is like our agenda, and that is like the main, actually the main thing that we are actually doing. Good. So what follows next is actually this, a very deep revision into all the mathematics that we are going to use in this unit. Good news, you have already covered this one in the prerequisite courses. Okay, so you see how we have moved. We have revisited, we have talked about statistical versus classical machine learning. Now we're in this section, understanding statistical machine learning. And it's called the foundations of statistical machine learning. Something from René Descartes there, you can read. The theory of dualism is a very powerful theory. Okay, fine. So what are we going to review today and on Monday? We'll start today and finish on Monday. This is what I want you to know, is that machine learning and AI is driven by what we call formal mathematical models. Okay, so I talked about a model. I told you what a model is. It is a representation of the real world. So we are going to look at formal models and theories. Okay, so these ones are normally called model theories of AI. If you get any machine learning book, it starts with mathematics, pure math, and then now it goes to the very things, because we can't do modern day machine learning without actually doing all this. Okay, so we need knowledge from all this. We start with statistics, we review it. We'll go to probability, we review it. We go to linear algebra, we review it. We go to calculus, we review it. We'll not review geometry and trigonometry and set theory. Set theory is the easiest. We'll just be mentioning as we go through. Why do we need all this? For example, geometry, why is it falling here? If you want to do computer vision, there's a lot of shapes and all these kind of things, objects, etc. That's where geometry comes in, and also trigonometry, etc. So I'll be telling you why we are reviewing all that we are reviewing. So let's take a very deep dive. Get your calculators and your writing pads. We are now going into, we start with statistics and probability. On Monday, we'll continue the linear algebra review. And then, so for the next few lectures, I'm going to sound like a mathematics guy, and I want that to be the music. And we are then going to tie that one now into our unit as we are doing it. So I want to start with the statistics. Go here and open the next one. So you might not have this one because it's not yet complete. So this one you just have to follow through with me. If it's not very clear, you ask me to zoom. Now it's loading. So you might not be seeing anything. All the way up there, some message I have. Yeah, in a moment. Guys are asking for a short break. We can rush to the kitchen and grab maybe something, maybe for 5 minutes, and then we come back. I will just leave my screen the way it is. My clock says, my watch here, 9:22, but it's usually in a different time zone. It's 9:30. We can come back at 9:35 in the next 5 minutes. So guys, let's take a 5-minute break or walk, say hi to the neighbors, etc. Back at 9:35. Okay, fine. So we are now back. I hope you can hear me. I want us now to go through some revision today, then we finish on Monday as we go on. I hope most of the guys are back. Yes, I can see everyone is still here. That's good. So now, we have already said modern day machine learning runs on statistics, probability, and a lot of math, and instead of symbols. So we are supposed to review all these maths so that we can be able to use it. So anytime you are using maths, we normally call that applied mathematics. And anytime you are just studying maths for the sake of it, is called pure math. So we start here with the stats and probes, and then I will tell you where exactly we are going to use all these things, etc. I will try to summarize, and I will be summarizing with examples, and I hope you are able to see the screen. I have zoomed to the very last, I think so. So let's start by reviewing statistics. It is the science of data. That's the first thing. It collects, analyzes, and presents and interprets data. Obviously, there's a reason now. We are seeing the reason why statistics is important. It's because it's the science of data. It deals with data. So very quickly, there are two branches of statistics: descriptive and inferential statistics. We'll discuss this in a moment. But before we discuss that, some 3 major terms in statistics. Number 1 is population. This is a set of all elements of interest in a subset of a population. Okay, and then there's a statistic, which is a quantity that is calculated from the sample. So a statistic is calculated from the sample. A sample represents the population in general, and you must have learned this way back. Then descriptive statistics. In is now the branch of statistics that tries to summarize data. So descriptive statistics just tries to summarize data. And the rest here will possibly read. This is where you find a lot of graphs and tables and all these kind of calculations for summarizing data. Inferential statistics, on the other hand, which we will use a lot, tries to make some conclusions about the population rather than just summarizing the data. So here it does a lot of estimations and tests a lot of hypotheses. You can remember our function is like a hypothesis, and you'll be able to see that. So the difference between inferential statistics and descriptive is that descriptive, even from the name, describes data. Okay, it tries to summarize data. Inferential statistics, from the word infer, it tries to make sense out of the data. It's like more intelligent than descriptive, though that definition is not valid. Okay, fine. So very fast, what is data in statistics? Because it's the science of data. Data are facts and figures, of course. Then data contains attributes. Okay, so these attributes, you're going to call them features in AI. Then you can have a group of data that is now called a data set. It's a collection of data. Now, you're reminded that data can be classified, number one, based on source, which can be primary or secondary data. Primary data is the one you collect yourself, like we're going to see. It's very important in documentary number 2. And secondary data is that which exists, that you just take and you train your model with. Then data can also be classified based on nature. So it can either be qualitative or quantitative data. Okay, so qualitative data just has things which are actually not numbers. Okay, and quantitative data are actually numbers, which can be discrete or continuous. So you don't have to cram those ones. Those are just things to follow up. Now, the most important thing I will point here is that data has scales. Okay. Data has scales. So a scale is used to quantify variables in a data. And there are 4 important scales that we are going to look at that you must know. And before we look at those 4 scales, is that they are what we call properties of a scale. Okay, there are some 4 properties of a scale. So a scale, any given scale has either one or more of these properties. Okay, property number 1 is that the scale has an identity. This just means that every measurement is unique from another measurement. We are going to see an example. A scale also has a magnitude. Okay, the difference between values, which is called the equal intervals, and then there's something called an absolute zero, the properties of a scale. But now the focus is actually here. These are the 4 scales that you're supposed to know. The first one is called a nominal scale or nominal data. This one has identity only. It gives variables a descriptive data. There is no magnitude. For example, if I have data on gender and guys are categorized as male or female, there is no numerical difference between a male and a female. It is just an identity difference. I know a male is a male and a female is a female. That data does not tell me whether I have 2 males or 3 females, etc. It is called a nominal scale, a scale that has only identity. Another good example here is when I have yes, no, neutral data set. It's also a nominal data set. Then number 2, there is what we call an ordinal scale. Okay, these has both identity and magnitude. Okay, the other best way of thinking of ordinal scale is that it gives orders. Okay, there's some order. There's like a hierarchy or category. Okay, so it has both identity. For example, here, temperature can either be hot, mild, or cold. Okay, so we already know hot. Somehow, hot seems to be a bit higher than mild. which seems to be a bit higher than cold. So there's some form of a magnitude here. But important here is that ordinal data usually has some order, okay, and there's a rank kind of. Now here we don't have like intervals. I can't say the difference between mild and hot is 30 or 20 unless I'm given more information. So the next scale is called an interval scale. This has identity, magnitude, and intervals. Okay. Example, when I'm measuring temperature in terms of Fahrenheit or degrees, the difference between 40 and 50 degrees is the same as difference between 50 and 60 degrees, which is actually 10 degrees. Okay, so I have like an equal interval. So between 40 and 50, I have 10 units. Between 50 and 60, I have 10 units. That is usually called an interval scale or an interval data set. And then finally, we have now the most important, it's called a ratio scale. Ratio scale has all the four properties. It has identity, magnitude, intervals, and an absolute zero. I want to focus on absolute zero. Example of a ratio data set or scale is when I have weights of objects. Now, an object, when it has a weight of zero, it can never go below zero. You can never have negative weight. So absolute zero is like a true zero. As opposed to interval has no absolute zero. For example, temperatures can go up to negative 10 degrees. Okay, you see, there's no true zero as such. Though in physics, you could go to far extents. But now here in statistics is that the ratio scale is like the perfect scale. So when you have a ratio data set, you have the identity, magnitude, interval, and you have a true zero, which is an absolute zero. And you can find many examples to fit here. These four scales are going to be important because the type of data set that you have is going to determine the type of model that you can use, and it's going to determine how you prepare your data for the training purposes. The way I deal with ordinal data is different from the way I deal with ratio data, etc. Fine. So those ones are just reading and remembering. Then the next thing that we go to in statistics, unless there's a question, is the measure of central tendency. This is another thing you must have done in statistics. So measure of central tendency is like having a value that generally explains the data. Okay, one value kind of summarizing the data. This can also be called the center of a distribution of a data. Some of the things we use to measure or to find a value that describes the data are mean, mode, and median. Okay, the mean is the most famous here, such that the mean has different types of means. There is what we call the weighted arithmetic mean, there's a trimmed mean, there's a geometrical mean, and there's a harmonic mean, and these ones you can revise. But every data set, there's usually a way to try and summarize the data using a single point or a single value. That is the theory of measure of central tendencies. That's what a mean does. Then on this side now, here comes the importance of knowing the different scales. When do I use mean, median, or mode to describe the center of a data set or the center of a distribution? Okay, it depends on the type of data you have. Here is the statistical advice. So if you have nominal data, you cannot compute mean from a nominal data. Okay, so we normally use mode. If I have ordinal data, we use median. So you cannot compute median in a nominal data. If I have interval or ratio data, I can use either mean or median, depending on whether the data set is skewed or not skewed. We are discussing skewing in a moment. So the type of data that I have will dictate the type of central tendency that I can use. And that is going to be so important in machine learning, the type of data and the type of things we can measure in a data set. So just try to, I will upload these ones in a moment. Please go through these ones and then be familiar with them. The next thing in statistics that is important I want to point out to is the measure of the shape of a distribution. So what is a distribution first? So whenever you're given a data set, let's say we are collecting the age of ICS students, we will have maybe so many ages and they will fall within a range, let's say maybe between 18 and maybe 25. So we will have values distributed along that range between 18, the minimum maybe, and 25, the maximum. Then when we are doing this, we'll actually have, let's say we have 100 students that we are counting. So maybe we'll have, so that is the range, maybe let me use 18 to 25 as a range, 18 minimum, you can write that one down, and 25 maximum. Our values will be distributed in here. So let's say within 100 people, let's say we are counting the value 23. Amongst 100 people, we'll count the value 23 maybe 10 times. So we usually don't write 23 10 times. We write 23 alongside its frequency. The frequency is how many times have we counted 23. So that's why you're seeing this distribution is normally drawn using a frequency. Okay, so there's usually a frequency here, and then the x values are actually down here. The x values are the ages that we have down here. Then let's say most of the students have the age maybe 22. So 22, there is going to be a lot of, the frequency of 22 is going to be high because so many students have 22 as their age. And so that's going to define the high frequency for the value 22 within this range, okay? So a distribution is how the frequencies are kind of spread out within a range, okay? And that is going to mean different things as we go along. So now I have distributions normally look like this. There is a curve, okay? And here at the center is where a lot of concentration actually is. If I may get a pen and draw a lot of things here. Let me see this one. Yes. So you see here at the center, this is where most of the values are concentrated, okay? And where most of the values are concentrated, they are going to affect the mean. The mean will tend to be dancing around this area in a data set. So there's the frequency on this side, and then there is the data set flowing on that side. Good. So we call this a distribution. So what is skewness? Skewness is the measure of the shape of a distribution. You see the shape of this distribution looks like a bell. It's bell-shaped. We call this distribution a perfect symmetrical distribution. Symmetry just means a perfect shape. It's flowing. You can see it's like a bell-shaped. It's perfect. It's kind of perfect. So skewness is a measure of the symmetry in a data set. Symmetry is how this thing is flowing. This line is perfectly dividing this half and that half into perfect shapes and perfect halves. So skewness is able to measure how perfect or what is the symmetry of a distribution. Okay, it is called symmetrical distribution. They are all found at the center and they are all equal to each other. So the mean, which is written like this, is equal to the mode and it's equal to the median in a perfect symmetry. Okay. And is not skewed. There is no skewness here. or the skewness is 0, like we are going to measure and see. Then we go to the other side, we see there's a positively skewed data set. Okay. In a positively skewed data set, we have the presence of low frequency observations on the right. Low frequency means that here you can see frequencies are pushed downwards. Okay, so low frequencies are concentrated to the right. Okay, we call this a positively skewed data set. Okay, this is positively skewed. If I may try, I will get a better board. Positively skewed. So in a positively skewed, the graph tends to lie towards that direction. Okay. And here, the mean, median, and mode are not equal. The mean is greater than the median, which is greater than the mode. Okay, in a positively skewed data set. Okay, so this is positively skewed. Then we finish by checking a negatively skewed data set or distribution. I'll be using the word distribution. In a negatively skewed distribution, low frequencies are concentrated on this side. Low frequencies means that, and this is data set like that. So low frequencies means that the curve will hit lows on this side. So we call this a negatively skewed data set. Okay, so in a sense, skewness is trying to measure the shape of a distribution. These are the shapes we are talking about. And in negatively skewed, the mean is less than the median, is less than the mode. You don't have to cram, we just have to apply these ones. So how do we compute these things? How do we compute skewness of a graph, which we are going to do in a moment? So before we compute skewness of a graph or of a distribution, I'm going to introduce the moments of a distribution. What is the moment of a distribution? So the moment of a distribution is defined by this formula. You can have it somewhere because this is what you're going to use. The moment is defined by this formula. Let me zoom in and then go to this side. Good. This is just saying we will take the x values minus the mean. We'll do this. We'll capture it as we do it. And then we'll raise it to a power r. And then we will take summations. And then we'll divide everything by n, etc. In short, for now, the moment of a graph or of a distribution is defined by this formula. And r is made up of these numbers, integers, positive integers. So if r is 0, the moment is always a 1. If r is 1, there's a value. If r is 2, the reason why I'm pointing out this one because it is special. If r is 2, the moment will always be sigma squared. What is sigma squared? Sigma squared is also the variance of the data set, which will actually be easy to compute in this format. So the second moment of a distribution is always its variance. Okay, so when you're asked to compute the variance, you just compute the second moment of a distribution. And we are going to do this in a practical way. There are other ways to compute variance, which I don't concentrate on. You see, the moment is so important because R is increasing. The more I go to the third moment, fourth moment, fifth moment, I get a lot of statistical formulas just from the moments formula alone. So it defines a lot for me in my statistical package. So let's go down here for a moment. We are also discussing moments, and we are taking moments for a moment. So how do you measure skewness? Whether a graph or a distribution is positively skewed or negatively skewed. The way we defined moments up here, freezing. This sign here is a Greek letter called mu, mu, mu. So the mu of R, or we read this as mu sub R because R is a subscript here. So anytime you see the mu, we are just trying to say the moment of. Okay. So I write here, let me see. Okay, just a moment. So when I write mu sub 1, I'm just saying the first moment, okay? So we are going to note a number of things. You can write them down. For a symmetrical distribution, symmetrical means perfect, the bell-shaped curve with no skewness. All odd moments are equal to 0. What does odd mean? A 3, a 1, okay, a 5, okay, they are all equal to 0 if the distribution is symmetrical, all equal to 0. Then note also that the first moment of all distributions is also equal to 0, the first moment. We are going to apply this, not to cram. Skewness is defined by this formula. Okay, it is always called beta 1. Okay, when I write mu sub 3 squared, I am just saying the third moment squared. So if you want to compute skewness of a graph, I will compute the third moment, I will square it, then I will divide it by the second moment cubed. Second moment cubed, first moment squared, okay, etc. Then I will take the sign of the skewness, positively skewed, negatively skewed, from the third moment. If my third moment was negative, I will say the data set is negatively skewed. If it's positive, I will say it's positively skewed. This is well understood by doing examples. So we are on into our example 1, which might define a lot for us today. Fine. So we can have this example. You can look at it. Compute the variance, standard deviation, and skewness of the following data set. So this is the data set. Let's say I'm given 0 to 10 as a frequency of 6, 10 to 20, 12, and so on and so forth. Then I am asked to compute variance, standard deviation, and skewness, whether this distribution is positively skewed or negatively skewed. So we are going to go through this together very fast. We normally make a table like this one. And then we have the classes here, the ones we are given, and their frequencies here. Okay, this is the summation of all frequencies. So it means in this data set we have 100 items. Okay, and then the rest of these ones are just mine, kind of. So the statistical knowledge is the mean of this data set. That's my first practice to you. So if we were in class now, I could just be walking around as you compute the mean. Let's try to compute the mean. Then someone tell me, by the way, how do we compute the mean from your statistics knowledge? Someone who really passed this statistics thing can call in and then tell me. Anyone who remembers the formula for the mean of a data set? Forgotten. I want you to try. Compute the mean in 1 minute, then you share with me. Yes, Waweru.
Yes. So
hello.
For the mean, calculating the mean, it's usually a summation of the frequency and the mid values over the summation
Yes.
of the frequency.
Very, very good. In other words, it's summation of fx divided by summation of f. Very right. That's why I left out this column. These are the f's we are talking about. These are the x's. So there is one column you might need here where you multiply the f by the x. So 6 times 5 will be 30, 12 times 15 will be so and so, and then that will be your column for fx. You will add everything in fx, then you will divide by 100 for f. Anyone who is good at working faster, who has found a value?
35.
35. Very good. The value is 35. So the mean is 35. Okay. And now when I have a mean of 35, I just want to go quickly down here. These ones, by the way, will be coding. We'll be coding these ones, or we'll be using the, what do you call it? The libraries already have these formulas, but we are expected to know. So if I may zoom here a bit, you see the formula here says x minus x bar. X bar is always the mean, okay, the mean. So in short, you take individual x's, will minus the mean, and so on. That's just how the formula goes. But due to the flow, so here is what we have. Here is what we have. The mean is 35. So what did I want to point out here is the following, is that we have this column here where we're just taking the deviations from the mean. Okay, so we're just saying x minus 35. And to simplify things, we're just dividing it by 10 so that we have smaller values. And then after we call that column a u, you can call it anything. Then we'll have another column called fu, then another column called fu squared, because we want the second moment and we also want the third moment, where you just cube the values. Okay. Then we will get to 60 here after summation, and 48 here after summation, and 0 here after summation. So how do I get the second moment? According to the formula, this is the calculation I was able to do, is that number one, the mean is 35. Okay, I'll post this one. Number two, the second moment is made up of, if you can remember, let me go all the way here. Okay. So the formula is here. After taking deviations from the mean, I raise it to the power, so it's the second moment. I do the summations, which we have already done in the table. Then we're supposed to divide by n. Our n is 100. We have 100 items. So that summation and blah, blah, blah was done here. That's why we have 260 down here. So the second moment will actually be 260 divided by 100. Okay, it's very easy to compute, by the way. Formulas scare people. That's why some guys ask, can you explain things easily, or are you a mathematician? Because they explain with a lot of notations that are not actually maybe important sometimes, but they're important also. So 260 divided by 100, but because we simplify things here, we are also going to multiply by 10 squared because of we're in the second moment. Here we will do 48 divided by 100, and then we will cube. We'll cube it. But even if you don't cube or square, still the answer is supposed to be the same. So what do you end up with? You will end up with the following. Second moment of a graph. So the moment you find the second moment, that's our variance. So 260 over 100 times 10 squared, which is 260. Is a question. Yes, Anita. Okay, maybe her mic is on. So you'll find 260 here. Then the standard deviation is usually the square root of the variance, so it's easy. The third moment, find it to be 480. So the skewness is the third moment cubed divided by the second moment squared. And then you're actually now able to find this value. So this value defines the skewness of that curve without drawing it. So because the third moment is positive, remember the sign, and the B1 is a small value, 0.01, therefore we just say the distribution is slightly positively skewed. That is the answer for the skewness of this curve, okay? And the formulas, we will always have them, and we will now be applying them. That is like the thing. So here is like something in the intelligence corner. If you find a value that is less than 1, you say it is highly skewed. If you find a 0, that is a perfect symmetry. So it is perfectly, no, it's not perfectly skewed. It's a perfect symmetry. I will change this one. We find the value to be 0.5 minus 1. No, 0.5, between 0.5 and 1, I will say it is a moderate skew. That's what we are saying here. We found 0.01. If you find a value greater than 1, we say it is a very highly skewed value. The sign is found by the third moment. The third moment here is 480. 480 is a positive number. So we say the data set is positively skewed. So do we have any question right there on skewness?
I have a question.
Okay, so the example. Yes. Let me see. Who is it?
Waweru.
Yes, Waweru.
Yeah. For the parts, the U column.
The mu.
Why? It's mu.
The U column. Yes.
Yeah. So.
No, it's U. Now the problem is that we normally confuse mu and U. That's just a U. We can use a V, a T, a W. Okay, just any letter.
So for that column,
yes,
you've done x minus 35 over 10.
35. Yes.
Over 10. Why over 10? Okay, please explain that column.
Over. Very good. A good question. Okay, I'll explain. So over 10, let me zoom again. This over 10 is just something that I do just freely in order to simplify. So ideally what should happen here is x minus 35, just like that, okay? X minus 35, like here we take 5, sorry, it was supposed to be 5, minus 35, you get negative 30, right? So here we should have negative 30, negative 20, negative 10. But now I just use divide by 10. It won't affect anything so that I have small values here. And then later I will recover this 10 later in my multiplications. But ideally, you can play around with this column. People normally play around with this column. You can divide by 1,000, you can multiply by 60, provided that whatever you do here, you do the opposite when you're recovering this value. So how did we do the opposite? Because I divided here by 10, when I was finding the second moment, right here on this other side, when I was finding the second moment, you see now I'm multiplying by 10 squared here, and in the third moment I'm multiplying by 10 cubed. If I had divided by, let's say 6, I will multiply here by 6 squared and by 10 squared. If I never divided by 10, I will have some larger values here, and I will still get this answer by the end of the day. So it's just a way to simplify computations in a column, etc. I hope that is a bit clear.
It's okay. Thank you.
Yeah. Okay, welcome. Any other question? I see our time is much spent. So I'll just mention where we will pick it up from, and then we'll post these ones as we continue. So finding the moment is easy. You just do a few calculations to familiarize yourself as you revise. and then we will actually be applying these things. So after finding the moments, there are other ways of measuring the skewness of a graph. Okay. These are like the following: the Carl-Pearson coefficient, Bowley's measure, and Kelly's measure. I don't use those ones. I just use the moments, which are actually perfect and easy. The moments. Then let's finish with this one very quickly. There are two ways to measure the shape of a curve. Number one is to measure it using symmetry, the one we have looked at. Then number two is to measure it using kurtosis. Okay, so kurtosis is the other measure of the shape of a distribution. So these are just two slides. We finish with this one. So skewness measures the lack of symmetry, whether it's skewing to the left or to the right. But kurtosis measures the height, okay, or the peakedness, the peak, okay, the peak of the distribution, okay. It tries to measure the peak of the distribution. How high is the distribution going, okay, and so on and so forth. This is going to be so important for us. So there are three shapes. The first one is called leptocartic. Okay, that is the highest. Sorry if you're seeing that on my screen. The next one is mesocartic, which is the moderate. And then finally, is platycartic. So we'll just be using these terms, as we are not going to be doing exams on this, but using these terms as we describe our data set. So very quickly, remember we measure skewness using beta 1, okay? We measure kurtosis using beta 2, which is easy. It is just the fourth moment of the distribution divided by the second moment squared, okay? Fourth moment divided by the second moment squared. Someone is raising the hand. Yes, Newton. Is there an issue? Or maybe he has pressed wrong button. So this is the summary. If you find beta 2 to be equal to 3, then the distribution is mesocartic. You'll just be coming back here and checking mesocartic is the standard, okay? If you find beta 2 to be greater than 3, it is leptocartic, okay? It's very high. It's hitting high frequencies. If you find beta 2 to be less than 3, it is platycartic. So it is a nice low frequency data set, okay? And those are going to be some special terms that we are going to be using. So very fast, this is an easy example. I want us to try it out. I don't know if you can see. I'm zooming until I'm losing. So I want us really to do this before we end the class. So please try and do this. The first four moments of a distribution are 0, 2.5, 0.7, and 18.75. Examine the skewness and the kurtosis of the distribution. I want us to calculate this one from the formulas I've already given you, and then try to tell me. Finding beta 1 and finding beta 2. Beta 1 defines skewness, beta 2 defines kurtosis. And yes. So calculate, then if you find skewness, remember skewness also has a sign. It can be positively or negatively skewed. I want you to find also the sign. The sign is given by the third moment, which is also part of the equation in beta 1. For kurtosis, there's no sign. You just have to check. Do I have a 3, or is the value greater than or less than 3, etc. Yes. So calculators are running now. Anyone who can see this? I hope everyone can see. There's something on the chat. Let me see if there are questions there. As you guys calculate, of course. Someone is worried about the cut. No, we are going to apply this. I won't ask you maths questions. I will ask you machine learning questions. Now there are application of this. So I want us to review this. I don't want you to cram. I want you to follow through. We are going to use a lot of this. I'm not going to ask you to calculate skewness and kurtosis. No, but we will apply. I want you to understand where actually we are going to apply this. Salome, maybe you can rephrase the question. You're asking why did we get 3 moments? I'm not sure where that was specifically. Are you okay now or you're fine? You can just comment there. You'll see it. Very good. Salome already has the solution. Newton also confirmed that he's okay. Anyone to call in and tell me what you have? Or you already have the numbers down? I go back to the formulas. You have forgotten the formulas. I didn't post because I wanted guys to calculate before we check like the answer. Okay, so this is the formula for getting skewness. The third moment squared divided by the second moment cubed. Anyone who has beta 1? We used to calculate very fast back in the days. What happened? Edmond, are you around? Are you fine? Edmond is around. Okay. Steven, anything from your side? Yes, John.
Hello?
Yes.
Question.
You have found beta 1?
No, I'm confirming the
Yes.
formula. Which one is
Yes.
Q?
You can see my screen. It's here. The third moment is squared. Okay, and it's up here. And the second moment is cubed, and it's down here.
Okay.
I hope now this one is visible. I've written a lot of things here. You've seen that? Austin?
Yes, it was the same question. So what we had earlier gotten in the previous example is wrong at some point.
We changed some numerator and denominator.
Yeah, in the
where was the wrong part?
In finding the skewness for the data we had the previous example.
Yes. Yes.
Where
was the wrong part?
You cubed the third.
Yeah. I think I noticed that one. Yeah, very true. I cubed where I should have squared, right?
Yeah.
And I squared where I should have cubed.
Yeah, true.
Yeah, true. Okay, fine, I will correct that one. Now, who has found this one? This current one. So for kurtosis, it's only the second moment that is square. The fourth moment, nothing happens. You just take it as it is, and it's called beta 2. Anyone? Yes, we have someone. Yes, Stacy, what did you find?
Can you hear me?
Yes, I can.
For skewness,
Pardon? It's like breaking a bit.
for skewness, I got a 0. Okay, let me change my connection.
Okay, or you can even comment on the chat. I'll see. Anyone else? As Stacy gets something. Vanessa, what have you found? I hope you're still there.
Yeah.
You can hear me?
Yeah, but I've seen, okay, I found
Yes.
031, and I can also see there's so many people on the chat who I think wanted to answer. But 0.031.
Okay, let me.
Yeah.
Okay, there are some answers. All right. Thank you for that. I was not checking. 0.031 positively skewed, and the other one is metic. Okay, fine. Okay, fine. That is actually good. I was worried. I was thinking we are already hit hard. The active class went, but I didn't know there were answers flowing. Either way, yes, fine. So the answer for B1 is actually 0.7 squared divided by 2.5 cubed, which is 0.031. And it's between 0 and 1, so we say it's moderately positively skewed. And for kurtosis, the answer is 3, so it is mesochatic. In fact, mesochatic is like a perfect curve because it sits in the middle. So this example was made on purpose, sits in the middle, etc. So we're just familiarizing ourselves with the terms that we'll actually be using. And with that, we end our statistical review. Our next review will just be on probability. And I think we can talk on this on Monday. We'll be talking probability, which is going to be the same style. We're going to calculate a lot. I don't know what's installing or uninstalling in my machine. I will check. We'll talk about random variables. I'll also talk about, we'll give examples and try to explain in the easiest terms probability distributions. Okay, I will tell you what those ones are. I will remind you. I will give good examples here. So apart from frequency distribution in statistics, we have probability distribution. Then these are going to form the heart of machine learning. I will talk about some important distributions that we are going to use. Binomial, Bernoulli, geometric, etc. I will explain what these are, Poissons, then other distributions are known as continuous. We'll talk about all this. And I will give more examples. We'll upload this one, by the way. We'll give more examples. Then what else will I say? I'll give examples, Poisson, binomial. We check the shape of probability distribution. You see, like Poisson, it is skewed, and it shares the same shape with binomial. So we say they are relatives, and they are related to each other. Yes. Yeah, I will talk about all this. And then I will go into what we call Bayes theorem, which is the heart of machine learning. And then I will be able to finish probability. So on Monday, we'll revise probability. And also check out the links at the e-learning. On top there, you can start watching. I will post some small assignments on those documentaries. It's very, very interesting ones. So don't view much. The hint here I will give is that don't view much as I'm doing this for the CAT or for the exam, but I want you to learn as much as possible. The CAT exam mostly will be centered around the tasks that we'll be doing. So I will tell you also, as far as those ones are concerned, where to focus. For now, that was any question or comments. So apart from the participation, and I know guys have been there, still you can comment with your admission number, student number that is, on the chat, so that we know all the guys that were there. So let the 91 chats now flow, and then we can call it a day for today. You can actually read ahead. I will be posting ahead so that you read ahead. And I will be flagging materials, by the way. Some we might not even use them, but for the purpose of those who actually need a lot to make good use of this holiday time. We'll be coding a lot and sharing a lot also. And that will be our semester. So thank you very much for today. Today we can rest it there, you can watch the documentaries, and if you have any questions, remember, on the attachment I'll be talking to you guys later on a different thing. Our WhatsApp groups remains, our class reps remain, and we are still going to continue in the best way possible. So thank you very much. See you on Monday.